Have you ever been sitting in a window seat, staring out at that massive wing, and just thought, how on earth does this thing work? I mean, really, how does this giant metal tube weighing hundreds of thousands of pounds just fly? Well, today we're going to peel back the skin of the aircraft and see what really makes it tick.
Just look at the sheer complexity of this machine. It's like an intricate symphony with millions of parts, and they all have to work together perfectly. And the person in charge of conducting this symphony? The pilot. They don't just know how to fly it. They have to understand how it works, from the inside out. They have to download a literal library of information into their brains.
And that's exactly what we're digging into in this explainer. We actually got our hands on an airline transport pilot license study guide. Think of it as the ultimate cheat sheet, the book of secrets, if you will. This is the stuff that future airline captains have to know cold. So let's crack it open and start with maybe the most basic challenge of all, the structure itself.
Okay, first up, the engineering challenge of structure. You see, when you're building a plane, you're in this constant tug of war between making it incredibly strong, but also lightweight, and rigid, but also flexible.
Yeah, it kind of sounds like a contradiction, right? I mean, if you've ever looked out the window during turbulence, you've seen those wings flexing up and down like crazy. They have to be insanely strong to create all that lift, but if they were totally stiff, the first big gust of wind would just snap them right off. So, what's the secret?
Well, the answer is hidden inside the wing. It's basically built around an internal skeleton, kind of like our bodies. Those long, super strong beams running the length of the wing, those are the spars. They're the backbone, taking most of the bending force. Then you have the ribs, which run perpendicular, and they give the wing that classic curved airfoil shape that actually generates the lift. Altogether, they create this incredible structure that spreads the load out.
But here's the real magic, and you can see it on this chart. It's all about the material science. The special aluminum alloys they use are engineered to have what's called a high elastic limit. What that means is you can put a ton of stress on it, what engineers call strain, and the metal will bend, but then it'll spring right back to its original shape when the force is gone. It's only when you push it past that limit, into the red plastic zone, that it stays bent for good. So that terrifying wing flex you see in turbulence, that's not a problem. That's the wing doing its job perfectly.
So we've got a structure that can fly without breaking apart. Awesome. But how does a pilot actually control the thing? That gets us to our next big engineering puzzle. How do you steer a giant with any kind of precision?
Back in the day, it was pretty much all about brute force. The pilot's controls, the yoke, and the pedals were physically connected to the control surfaces on the wings and tail with a whole complex web of steel cables and pulleys. You can see it right here. The pilot turns the wheel, a cable literally pulls on a surface, and the plane moves. It's super direct, totally mechanical, but on a huge modern jet, it would be insanely heavy and almost impossible to manage.
So modern aviation came up with a total game changer, fly-by-wire. And here's the key thing to get. There is no direct mechanical link. When a pilot moves the joystick, they're not pulling a cable. They're just sending an electronic signal to a flight computer. Then the computer figures out what the pilot wants to do and tells powerful hydraulic actuators how to move the control surfaces. It's basically the difference between pulling on a rope and sending an email.
And the benefits are just enormous. First, getting rid of all those heavy cables and pulleys means you reduce the plane's mass, and that saves a ton of fuel. The control response is way faster and more precise. The system is smart enough to detect and isolate faults on its own. And get this, it can even make thousands of tiny automatic adjustments every second to smooth out the ride in turbulence. That's called gust load alleviation. It's just a smarter, lighter, and way safer system.
Right, but all of these amazing digital systems, the flight controls, the navigation displays, even the coffee maker in the galley, they all need a constant supply of power. And that brings us to the challenge of electricity.
So here's a question for you. You know your car runs on a simple 12-volt DC battery, right? It works just fine. So why does a ridiculously complex, multi-million-dollar aircraft use AC, or alternating current? You know, the same kind of power that comes out of the outlets in your house.
And yep, the study guide has the answer. It really comes down to AC power just being way more flexible for this kind of job. It's super easy to change the voltage up or down with transformers for all the different systems. The alternators that make AC power are lighter and simpler than DC generators, and as we know in aviation, weight is everything. Plus, you can easily convert it back to DC for any systems that happen to need it. And here's a neat bonus. It's also better for sending information through wires for things like navigation systems.
Okay, so we've got a flexible structure, we've got computer-based controls, and an advanced electrical system. But all of this massive amount of complexity, has to be managed by a human being. So how in the world do pilots remember all of this stuff, especially when things get stressful? This is the human challenge. So, the study guide is packed with these little nuggets called exam tips. These are the things you absolutely, positively have to know. For instance, you ever see that little weight sticking out from the front of a control surface on a wing? That's called a mass balance, and its main purpose is to prevent something called flutter, which is a super dangerous aerodynamic vibration that can literally tear a wing apart in midair. It's a critical piece of safety, all boiled down to one simple, memorable fact.
But this is where it gets really cool. The memo tricks. These are the little mnemonic devices pilots use to lock in really complex ideas. For propeller systems, they learn oil fines. It's a super quick way to remember that on a lot of props, oil pressure is used to push the blades into a fine pitch, which gives them more power for takeoff. Oil equals fine. Simple, right?
And hey, remember that AC alternator we talked about? To remember how it works, pilots just use this little rhyme. Stator stays still, rotor carries field. The stator is the stationary part, and the rotor is the part that rotates and carries the magnetic field to generate electricity. It's just a quick little mental check to keep it all straight.
And let's circle all the way back to fly-by-wire. That system has multiple backup modes, and each has a different level of automated safety protection. So how do you remember the order? Easy. Normal to alternate to direct equals protections decrease. Normal mode has all the safety features active. If that fails, it drops to alternate mode with fewer protections. And in a worst-case scenario, direct mode gives the pilot raw, unfiltered control. It's a simple little phrase to remember a potentially life-saving sequence.
So there you have it. From the physics of a flexing wing to the clever memory tricks of the pilot up front, we've taken a quick flight through how an airplane really works. It's an absolute marvel of engineering for sure, but it's also a testament to the incredible knowledge and skill of the people flying these things. So maybe the next time you're buckled in and you feel that little bump of turbulence, you'll have a whole new appreciation for the hidden genius that's taking you to your destination.